All right, let's start. Good morning. So today I'm going to take attendance. Here's the sheet. Our job this week is essentially discussing sequences and their convergence and divergence. So somehow the notion of a sequence essentially is a function whose input space, whose domain is some subset of integers that is infinite. That's essentially the general definition that we're going to use. Surprisingly, on the one hand, it ends up being very useful to be able to use sequences for application purposes because you can encode a lot of information. For instance, in signal processing, it ends up being very useful. On the other hand, too, somehow, from a more intrinsic or more abstract point of view, too, we're going to be able to use sequences to discuss certain properties of functions, continuity, and other things. It turns out that a lot of limiting procedures that we're going to use in this class ends up being rather related to sequences. Before that, I want to do a couple of things. One of the first things that we should do is defining these notorious notions, supremum and infimum. These are going to be things that we're going to keep using throughout the course. And even before that, I wanted to mention a correction. So last week we were discussing this least upper bound business. Remember, this was one of the axioms. So completeness axiom for reals said that any bounded set of real numbers, insofar as it is non-empty, has a least upper bound. And we talked about what that means. It's the best upper bound in a sense, most optimal one. And I had given this as an example. We take S to be the half open, half closed set of intervals, the half closed, half open interval from 0 to 1, 0 included, 1 not included. And the point was that the least upper bound of this is 1. That was something that we discussed. So what do we need to do? We need to verify first that this guy, this 1, is indeed an upper bound. And second, it's the best upper bound. So this is the first item. I say, oh, if x is some point in S, then by definition, it has to be strictly less than 1, which means that 1 is an upper bound. Because if x is strictly less than 1, it is also less than or equal to 1, if you want. So 1 is an upper bound indeed. And then the second property, somehow we need to verify that, 1 is the best upper bound. And here I use the strategy of, well, if I were to try to optimize 1 so that I have a smaller upper bound, in this case 1 minus epsilon, this 1 minus epsilon, I want to say, fails to be an upper bound. Right? That's what it means for 1 to be the best upper bound. And so I take an epsilon. The correction is this, okay? Instead of Archimedean property, I should have said density of rationals, because that's technically what we used. What we said is, and again, remember, this density of rationals is another one of these axioms that we can just take for granted that govern numbers. Density of rationals, there's some rational number that is strictly between 1 and 1 minus epsilon. Well, by definition then, Q has to be within S, because S contains all numbers between 0 and 1. And so I was able to generate one point in S that is not upper bounded by this supposed better upper bound, which means that 1 minus epsilon fails to be an upper bound. In other words, the best upper bound has to be 1. So it's not a major issue to call this Archimedean property, density of rationals, blah, blah, blah. But I'm trying to give a good example, at least in class. Technically, instead of Archimedean property, I should say density of rationals here. But in a sense, these are pretty much the same thing. Not too complicated, not too sort of distinct from each other. Any comments or questions about this? What I could have done, I could have actually used Archimedean property here, but then the rest of the argument would be slightly different, because the Archimedean property says, given any real number, there is some integer that exceeds this real number. And so instead of invoking density of rationals, I could have here, alternatively, invoked the Archimedean property, which says that, well, there is some integer greater than 1 over epsilon. So this perhaps the trick, instead of, because I want to use sort of 1 over n really instead of n. And so if I take n to be some integer larger than 1 over epsilon, because if epsilon is small, 1 over epsilon is very large. Okay, this is some integer that is larger than 1 over epsilon. And then once you rearranged, it just turns out that 1 minus 1 over n is some, in fact, rational number again, that is strictly between this and this. And again, 1 minus 1 over n has to be in S again. So if I wanted, I could have used the Archimedean property or principle instead of the density of rationals here. They're pretty much interchangeable. Okay. Any comments or questions here? There is, in fact, a minor gap here. Again, it's not very important. I get the point here, like one gets what is being done here, and I'll leave it to you to really figure out what the gap is, identify it. But somehow there's a gap from here to there. Actually, this statement doesn't imply this. So there's a gap. Right from going from here to there, I'm missing some step, something here. Okay, I'll let you think about it. Like I said, it's not a major issue, but formally speaking, this is not completely correct. Okay. Any comments or questions? By the way, I started reading your first submissions and also the Google Forms. I'm generally very happy. I just looked around a little bit. I think I'm going to take some time, maybe on Friday, once I'm done with, reading everything, to discuss a little bit. Probably we're not going to have time to sort of discuss your feedback and certain problems for each problem set throughout the course, but I thought it would be a good idea to at least give you some idea as to what my perspective is. And to say the least, I do want to assure you that even though I may not discuss these things in class, I do read every single sort of feedback and sort of adjust how things go. Okay. So supremum and infimum, okay? Let's just focus on supremum. Infimum was pretty much sort of, instead of looking at upper bounds, you look at lower bounds, and that gives you the infimum. So let's just first focus on supremums. Here's a weird thing going on. Supremum is defined on subsets. So I'm going to say sup of some subset. And so remember from week 1, P or curly P of R is the collection of all subsets of R. Okay? So this is a function, but it's taking as inputs subsets. And so you take a set, you take a subset of real numbers, and then depending on the nature of A, you have a piecewise defined formula. So sup of A is the least upper bound of A in reals, right? It's a real number. If A is non-empty and it is bounded from above. Okay. We had discussed that this is essentially a consequence of the completeness axiom. Now, these two cases are somewhat edge cases. In the textbook, you're not going to see these two. So for some people, sup of a subset is not defined if it's not, if it is empty or if it is not bounded. In my experience, it's just a convenience to allow these values as well, and things just work out fine. And so I'm going to say if A is empty set, then I'm going to define the sup of A, in other words, sup of empty set to be minus infinity. And the third case is, well, the only remaining case is if A is not empty, but bounded, not bounded from above, in which case I'm going to define sup to be infinity. Okay, so sup for me is a function that takes subsets of reals, turns them into extended reals. So here's the idea. Here's the intuition. Okay. Say somewhere here is the extended real number, positive infinity, and then here's 0. Somewhere here is negative infinity. The first case is the most important case, of course. So if I have, let's say, something like this, okay? Let's say this is my A. We had talked about how to think of this least upper bound. I want to somehow clamp down on this set A. Okay? There's a right clamp and there's a left clamp. Sup is all about the right clamp. You start from positive infinity and you want to clamp down on this subset that you're trying to control as much as possible. So I'm going to keep pushing, okay? And then at some point I'm going to sort of get stuck, and that's my least upper bound. It's the optimal upper bound. Okay? If, of course, then A is empty, well, this guy is not here anymore. There's nothing. But still I want to clamp down on this set. Okay? So I start pushing, okay? But there's nothing stopping me. So I'm going to go all the way to negative infinity. That's why I'm defining the sup of the empty set to be minus infinity. Okay? But on the other hand, too, if A were unbounded in the positive direction, it's a bunch of integers, let's say, something like this. Well, sup of it then has to be positive infinity because if I push just a little bit so that I have perhaps a finite supremum, well, there's a bunch of points that I'm missing. So my clamp is missing a bunch of points in A. And so this is why, while this is the standard definition, I kind of extend the definition to these two cases as well.
So if it's not bounded from above, it's going to be infinity?
Yes, yes, exactly. Yes. In practice, what ends up happening is this definition allows me to not say, oh, let A be a non-empty and a bounded set, blah, blah, blah. I'm just going to say let A be a subset. Or typically what's going to happen is we're going to define a certain maybe function or whatever. And then we're going to look at a level set of it. Before worrying about whether or not this level set is empty, or rather non-empty and bounded, I'm just going to use the sup of it and stuff. You'll see where this comes in handy. Now, let me ask you this. So, any questions about this sup?
So is it like an operation that you perform on a set, or is it an attribute?
It's a function. It's a function as we defined. So sup of A is what I'm going to write. Okay. So for instance, here I would write sup of S equals 1. I'll write that. Instead of writing this LUB, which, by the way, you might see these things as well. And technically, in older sort of texts, people use like GLB or LUB, whatever. It's kind of like similar to GCD, if you're familiar with this. And OK, yeah, I'll see. I see it. Let me just write sup of S. So basically, I'm using the function notation, and I'm also telling you it's a function. It's a function whose input is a subset, output is a number, extended number. Yeah, two questions. Go ahead.
So supremum and infimum aren't affected by whether or not it's a closed or open bound?
No, no, exactly. Very good. So for instance here, if I looked at the, I'll write this, okay? That's a very good point. It's also not affected by whether or not the set consists only of rationals, in fact. So for instance, what I can say is, here, sup of 0, 1 equals sup of this equals sup of 0, 1, open intersection rationals. These are all equal to 1.
What did you say the inputs and outputs were something?
I'm saying here, when I write something like this, this kind of looks like f of x. That's all I'm saying, is this is just a function. I am using the function notation that it is a function. That's what I'm saying. It's just that the input is the whole subset. You had a question?
I forgot it.
Okay, sorry. Any other comments or questions? Now, if you do the same thing, but from below, you get inf. And I'll leave it to you to think about that, about the fact that these two sort of values are, again, consistent. Instead of trying to clamp down on your subset from above, if you try to clamp down on it from below, that's the idea of the infimum. So for instance, if you have the empty set, there's nothing stopping you from clamping down on A, so you keep pushing and pushing, and you go all the way up to positive infinity, because there's nothing stopping you. Okay. That's the general intuition. Now, these ideas, sup and inf, are related to max and min in a sense. But max and min, they are sometimes defined and sometimes they are not defined. And so we can write it like so. Let A be a subset. Then it's maximum and minimum are defined respectively by the following. I'm going to define the max of A to be the same thing as the sup of A, insofar as the sup of A is a point in A. And otherwise, this is not a defined expression. So let's say does not exist otherwise. And likewise, the relation between min and inf is similar. Min of A is inf of A insofar as inf of A is indeed a specific point in A, and it is not defined otherwise. Okay. Just to give an idea, for instance, while the sup of all three of these sets is 1, the max of this set is not defined, and the max of this set is not defined, but the max of this is 1. Okay, open interval, there's a sup, there's no max. Okay. Even if I were to take the rationals in it, doesn't exist. But if I were to take the closed interval, then the max is 1. So whenever max exists, it's going to be the same thing as a soup. But there could be situations where the subset is non-empty and bounded from above, but the max doesn't exist. The idea is, well, if you're looking at this half closed, half open interval, you're saying, oh, what is the largest real number strictly less than 1? The point is that there's no such number. Okay. Or you could also see, for instance, what is the smallest positive real number? There's no such thing. Okay. So that's the idea between distinguishing max and sup. So there is no such thing as the smallest positive real number. Okay.
Does that extend to positive rational numbers as well?
Exactly, yeah. You can use rational here too. Very good. This, of course, is because of everything that we assumed. There are systems, there is a branch of analysis where this doesn't hold. It is called non-standard analysis. So somehow they really sort of formally make sense of notions like infinitesimals and stuff like that. We're not going to do that, okay? But, there's like hyperreals, whatever. There's a bunch of things that you can use. We're not going to do any of that. We're just going to use the vanilla calculus approach. Any comments or questions about any of this? Yeah?
Does it also mean there is no the largest positive number as well?
Yes, you can say that too. Exactly. Now, we had talked about how to switch from the boundedness of sets, something like this, to boundedness of functions. We essentially want to do the same thing with sup and inf. So we're going to extend the notion of sup and inf to functions by just looking at their images. Okay. So I'm just going to say, let x be a set, and f be a function from x to reals. Okay. Then I'm going to define the sup and inf and max and min of f in terms of its image. Then the sup, inf, max, min of f are defined as those of its image. So for instance, I'll just introduce this notation. So for instance, you would see sup of f. This means sup of the image of f, which is the same thing as sup of the set of all those f of x's such that lowercase x varies in uppercase x. Okay. Instead of looking at the function, well, I cannot just really make sense of this. What I do is I look at the image. Because my function takes values in the reals, this image of f is a subset of reals, so I can just import the notion of supremum to make sense of this, and that's how I do it. Okay. Any comments or questions about this? Now, I realize this is like somewhat bizarre, sup and inf. Like I said, like this is the main boss of this course, really coming to terms with how to operate these. Okay. I want to do one proof about how these things work. Namely, I want to think about perhaps some sort of monotonicity property for this. What does that? What could that mean? Well, monotonous things are, well, if I had a function and if I'm going from left to right, an increasing function, for instance, would be something whose graph sort of goes up this way. I want to have a similar property with sup. But of course, in this case, my inputs are sets in and of themselves. So it's not going to be less than or equal to, but it's going to be rather subset of. I want to say something about what happens if I enlarge a set. How does the sup change? Okay. And so here's a claim about that. I think this is part of a theorem in the textbook that our author leaves as an exercise. So I'm going to do that exercise technically, but this one ends up being rather useful indeed. So I want to say something like this. Claim let A and B be two subsets of reals. And let's say A is a subset of B. Oh, I'm going to say A and B are two subsets of reals. If A is a subset of B, then, well, I want to relate the sup of A to sup of B and inf of A to inf of B. Then I want to say, I'll just first write down what I want to relate. Okay. So I want to put a relation here. This is a number or extended number. This too is an extended number. And so are these two. So I want to say either they're equal or this is smaller or this is smaller. And same thing with inf. Any guesses as to what I should put here in the middle? If A is a smaller subset than B, which of these is larger? Or can I say anything?
Supremum of B is going to be larger.
This is going to be larger. Okay. Any other, perhaps, guesses? Maybe you can say a couple words about why you think this is true.
Well, I guess if B is a subset of A, then it could technically be A, and so you could take off some of the lower portion of it, so it could be equal. So the highest point could still be equal to that of A, but you could also take off part of the highest part of A and just have the lower values, and so then it's going to be less than the supremum of B.
That's essentially the right idea. Does this kind of make sense, what your colleague is suggesting? Maybe let's try to be a little bit more explicit before writing the proof even. Well, okay, so these sups and infs, they're all defined for all subsets essentially, but whatever this inequality is, it should work for intervals. And intervals are easier to imagine, okay? So what I'm going to do is I'm going to think about intervals. So let's say, take these two. And I'm not even going to use numbers and stuff. I'm just going to try to visualize. Okay, this is my real line. I have a smaller interval. Let's say something like this. That's A. And then there's a larger interval that contains it. Now, your colleague mentioned certain situations where perhaps things get a little bit more complicated. But let's just imagine a situation like this. So somehow A is like pretty much in the middle of B. Okay? Now, sup of B, right, this right-hand side, is the best upper bound for the larger set. Okay? So it's basically this. And it seems like sup of A is to the left of it. Okay, so this is the positive infinity direction. Does this make sense? But of course, the point is that the claim is not specific to intervals. So we're going to have to really think about this image and sort of abstract out some sort of a proof that we can actually write. Does this make sense, by the way, that if this is the configuration of A and B, the upper bound, best upper bound of B should exceed the best upper bound of A? Right? Because I'm starting from positive infinity and I'm trying to clamp down on B and stuff like that. And before clamping down on A, I have to first clamp down on B, necessarily, because B is a larger subset.
They can also be the same, though.
They could be the same, yes. But, you know, when A is equal to B, it's harder to come up with an inequality. You're right, of course. Another more complicated situation would be if this smaller interval was flushed to the right. So in principle, A could be smaller than B, but their sup could be the same. That's true, yes. Part of the challenge is to come up with like a representative, nice caricature that perhaps you can reverse engineer. Okay. Any comments or questions about this?
It is very interesting that you just mentioned the sup or inf is the image of some function, right? But that drawing, you sort of lump them together.
Well, I mean, yes, but so I didn't represent sup and inf in this picture. What I should perhaps say is, so for instance, this would be the sup of B in this picture, and this would be the sup of A. Assuming that this goes over here.
So that is a particular value, right?
Yes, it's a number, yes. Yes. If you want to, if this doesn't make sense to you, you can say something like this. So A is maybe, I don't know, 0, 1, and B is minus 1, 2. This corresponds to this. And in this case, this would be like 0, 1, and minus 1, 1, if you want. If this, you know, coming up with numerical values work better for you, you can go ahead and do that. I am more of a visual person. I can't really think about numbers that fast. For me, it's, you know, visualizing these shapes is easier. So I tend to sort of gravitate toward these, but you can do that as well. Okay. Now, to be clear, this is not a proof. I'm just trying to figure out even what the claim is. Okay. And so, but you know, if what these two caricatures seem to point to is right, then this should be the other way around. The inf of the largest set should be lesser. When you're clamping down from the left, first you should be clamping down on B because it's larger. Okay? So that's the claim. Okay? We need to prove. Now, to be perhaps a little bit more formal, because I have defined sup and inf in this more general sense, my intuition really points to this idea that perhaps I should be first doing a case analysis. Either A is empty or it is non-empty. Because if it is empty, then things are going to work out straightforwardly. So this is sort of like an edge case I need to technically deal with. Either A is empty, XOR, right? Exclusive OR, it is non-empty. Okay. Let's call this case 1 and this case 2. Now we're going to handle both of these cases separately. In the first case, well, by definition, sup of A is minus infinity, and there's nothing to prove. And inf of A is positive infinity, and again, there's nothing to prove, because this is going to be an extended number, and any extended number is greater than or equal to minus infinity, for instance. Okay? Sup of A equals minus infinity, and inf of A is positive infinity. And so the claims are correct, what you might say, trivially. Or you could say, so there's nothing to do. So we're done with case number 1. Case number 2 is where the meat of the proof is going to be, really. In the second case, you see this time in case number 2, because I'm assuming that A is non-empty, I can take a point in A. Now that is allowed. If I didn't know at this stage that A were not the empty set, I couldn't just say let X be in A. But since in the second case I'm assuming that A is non-empty, I can go ahead and take 1 point. I don't know how many points there are in A, but I know that there's at least 1. Okay? So case 2. What we can do is this, okay? Let X in A, okay? So for instance, in case number 1, this would be a contradiction. Okay? But since A is a subset of B, X has to be in B also. Okay. Well, in particular, for instance, I know that B is not the empty set. Any set that contains a non-empty set has to be a non-empty set, for instance. So B is non-empty. I have 2 cases again. This time, depending on whether or not B is bounded or not, I can sort of go ahead and do this case analysis, but I might as well do something like this. Then by definition of sup and inf, I have this. I'm allowing the possibility of B to be unbounded. This still makes sense. And likewise, x is bounded from below by inf of B, which is minus infinity. I should have said plus infinity here. OK. But then this really says that sup of B, this extended number, is an upper bound. Either it is infinity, in which case it is not technically an upper bound, but in which case there's nothing to do anyway. Or it is a finite number, in which case sup of B is an upper bound for each A, for each x in A. So inf of B is a lower bound of A, and sup of B is an upper bound of A. Now the final stage is to use the definition of inf of A and sup of A, in that inf of A should be the best lower bound. If inf of B is a lower bound of A, inf of A can only be a better lower bound. In other words, it can only be greater than or equal to inf of B. And that is the end of the proof. This step, so this is not a very technical proof. It's not a very deep proof. So this last step is rather mind-boggling. This idea of, oh, I have an upper bound, but then the sup is the best upper bound. When you're trying to use this idea in proofs, it does kind of get bizarre a little bit. So the point was this, OK? I basically took this idea. I said, oh, sup of B is going to be an upper bound for A, the lower, smaller subset. But then sup of A, by definition, has to be the best upper bound. It has to be the optimal upper bound, meaning it has to be better, possibly, than sup of B. It cannot be worse, to say the least. Does this make sense a little bit? So this is a formal proof, and it corresponds to this.
The way you prove it
Yes.
is not part of the four formula you gave us, right? Proof by direct proof, contradiction.
No, this is a direct proof.
This is direct proof?
Yes, I only use the definitions of things. Although it doesn't matter what you call this at the end of the day. Like ultimately, I gave you all these logical things and so on so that you can parse things down. But in practice, people don't say, oh, I'm going to use this method now. And I don't want to mix it and stuff like that. This is like a more fluid thing. It's something like this, right? So when you're math is like poetry, OK? So when you're doing poetry, grammar is somewhat important, but it's not the most important thing. And we're going to sort of relax things a little bit. Just because it's not in the grammar book doesn't mean that it's not applicable.
So is it the same to use a set as a subset of one as saying it's less than?
So you're asking about sort of really thinking of this relation as something similar to less than.
Yeah.
Yes, you can think of this subset of as a relation on the collection of subsets, in which case that would be not quite a total ordering, but it is what is called a partial ordering. So this is a partial ordering relation, technically speaking, this subset of.
Is it possible for A to be a subset of B, but A is larger than B?
No. I mean, when I say larger, I mean B is a superset of A. Yeah. So when I say smaller and larger, and when anyone says that, they really mean this. One is a subset of the other one.
Okay.
At least at this stage.
Okay.
Any other comments or questions? Like I said, this is going to take a while. When you see someone else do these kinds of arguments, it looks rather straightforward, but you're going to see in problem set 2, it's going to be, cumbersome somehow to argue these kind of things. In my experience, that's how this works. Okay, so this is all I want to say about sup and inf. We're going to keep using these. What I want to do now is to define the main actor of this week, namely a sequence. Now remember, we had this set theory axiom, which basically said that everything, any type of object that we're dealing with in this class, eventually is a set. Then we talked about relations, a relation being the graph of a function, and then we switched over to functions. So a function is ultimately a specific type of a set, if you want. And a sequence is going to be a specific type of a function. Okay? We're just going to sort of define certain things in terms of these things that we defined so far. Definition. Let X be a set. A sequence in X is a function say in the set of all functions from positive integers into X. I'm explicitly defining a sequence to be a function. Okay. What's the point of doing this? Because you don't want to say, oh, let this be a function with integer input, whatever. You sort of, instead of saying all this stuff, you just abbreviate and you say, it's going to take a sequence. Okay. So at this stage, this looks like a benign definition. And it, in a sense, is. It's very useful, but once you get the hang of it. The notation I'm going to use, instead of f of n, perhaps, I'm going to use this bullet notation. Denoted by x subscript bullet. Okay, and I can write it like so as well. So this is going to be a special notation for us. And I want you to really think of this, the input space, specifically for sequences as your discrete time. So this is x bullet. This is my time. This thing is going to be time. Okay. The point of using this x bullet notation is to say, oh, x is, how I'm thinking of it is like this. X is a point in X that depends on time. It moves with time somehow. I really want you to think of this x bullet, a sequence, to be a dynamical object. It's not one thing, it's something that moves within X. Okay? We're going to stop here for today. Tomorrow we're going to continue. Thank you. All right, let's start. Good morning. So at the end of last class, we had defined this new object sequence in a set. So today I want to discuss more about, say more about these sequences. We're going to spend some time. There are certain major theorems that are very useful in calculus when it comes to sequences. Before going into all that, though, what I want to do is I want to perhaps talk a little bit about some important examples that you should keep in mind. So in this class, certainly we're going to be worried about sequences of numbers, real numbers, but we're also going to be worried about sequences of functions. And I would argue that sequences of functions are more central to our cause. So if I have a set x, a sequence in x is nothing but a function that I denote by x bullet that goes from positive or non-negative integers into x. In principle, that you start indexing at 0 is not that important. We'll see in the examples. Instead of 0, it could be any other integer also, or some n integer. It doesn't really matter. There's a couple different notations for sequences. Question? Good. There's a couple different notations depending on the area that you're looking into or the textbook, whatever. I think in the textbook, this is the notation they use. So x sub n with curly braces, but they put a subscript n here to denote this is not just one point in x, it's a bunch of points somehow. You could see sort of x bracket n or x bracket bullet or x sub n in curly braces and stuff like that. Or you might see something like this, x sub n in parentheses, but then n goes from 0 to infinity. There's a bunch of notations. I tend to like this more, and as time goes by, I'm going to try to justify why perhaps this could be a nicer notation. The point here is that, like I told you last time, I want to think of this as my time. And here, n is supposed to be a dummy variable. So if I don't need to specify the sort of time parameter, I'd rather not call it a thing. Because what's going to happen is we're going to start looking at things like subsequences. I'm going to mention that in a second. I'm not going to define it exactly. But so for instance, if you look at the textbook, you're going to see things like x sub n sub k sub I sub j. So the subsequences ends up being sort of complicated to write down. So somehow I got used to using this bullet notation that allows me to just suppress all these index management stuff. So we'll see. Okay. For now, let's just take it for granted. So I said, oh, this is a function. And what does this mean? Ultimately, it means that instead of writing x of n, that's how we use functions, I'm just going to write x sub n. But n is arbitrary in essence. Don't worry about this notation for now. So there are certain modifications or certain ideas that sort of build on top of this more general definition, right? I can just take a sequence in any set whatsoever. But in order to be able to do some calculus, we need certain things. The first thing is going to be modification on time. One of them is going to be, well, we're going to take a sequence, and then we're going to take subsequences of it. So a sequence is a temporal, it's a dynamical object. It's not a set. I don't want you to think of it as a set. Even though functions are ultimately sets, it's not a set in x, is what I'm trying to say. It's something that changes in time. And so a subsequence will be something like editing out certain behaviors that we don't want to see. I'm going to give you the precise definition of it later. A slightly less useful idea is this derangement, which is when you jumble up the notion of time or the direction of time, and things sort of get more complicated. There is one instance in the textbook where this is used, which is this Riemann rearrangement theorem. It's about adding infinitely many terms, but somehow changing the order in which you add them to get different values. While it's an interesting matter, as far as I'm concerned, it's not really central. So probably I'm going to be skipping it, this Riemann rearrangement theorem. But people do these kind of things. This is not a natural thing to do, I want you to think, when it comes to sequences. On the other hand, on the direction, on the part for time, for space rather, if you have certain extra structures, we can do certain modifications on the sequence. So for instance, if you have some sort of an algebraic operation on x, imagine this is like reals, what we can do is, given the sequence, we can start tallying up. These are what is called the sequence of partial sums, for instance. Or we can average, or we can do sort of moving averages, whatever. We can do a bunch of things. We can multiply two sequences insofar as on x there's a multiplication and so on. We can do a bunch of operations like this. And another way x could have a structure is if it has what we're going to call a metric, or more generally topology. We're not going to discuss topology this much in this course. Then we can talk about convergence or divergence of certain sequences. Okay? I'm not going to go any further than this for now. For the rest of this class, most of this class, I want to give examples. But I want you to perhaps, have these in the back of your heads and sort of try to imagine what more can be done, in a sense. OK. And then, if time permits, I will start discussing this notion of a metric. So first, let's start with something like this. First example, x bullet. Okay, into R. Okay, that's going to be a sequence. Say n equals 1 over n. So at time n, x sub n is 1 over n. So if you want to be more formal or more explicit, remember this just means for any positive integer, x sub n is defined as the real number 1 over n. You can write it like so as well. Okay, that's a sequence. It's a sequence of real numbers. Okay, how do I visualize this? There are multiple ways. The perhaps first way of visualizing a sequence would be to just look at the space-time diagram. You write the horizontal, vertical, whatever. And even though the horizontal axis is supposed to be discrete, what you can do is you can just still pretend that it's the whole reals. Okay, so this is my time, which is this, and then this is my space. Right, so should be something like so. And then I can do this. So this is time 1, time 2, and so on. And so on. Okay. So for instance, let's think about this. What I can do is, certainly if I have a bunch of real numbers, I can add them up. And so based on this, I can turn this into a sequence of partial sums. Okay, so for instance, I can define S bullet, Sy because I want to say it's the sequence of sums. Send n to the sum of the first n terms. Okay. Now this is a different sequence, you see. And so in this case, S sub n would be sum from 1 to n of 1 over k. K is the dummy variable for this sum, right? And so this means that, for instance, I'll write it here. S1 is nothing but 1, because it's the first term only, remembering from the second week. S2 is 1 plus 1 over 2. S3 equals 1 plus 1 over 2 plus 1 over 3, and so on. That's a different sequence, somewhat related to the first sequence. Right? So the first sequence, I can say, is a sequence of terms of this sequence of sums, and vice versa. And so S bullet is the sequence of partial sums obtained by tallying the terms in X bullet. Okay. So somehow we would like to understand some sort of a metric. We would like to establish some sort of a metric in R, so that we can perhaps talk about the convergence or divergence of either one of these, right? Because somehow we would like to be able to say, for instance, that this guy converges to 0. Does this kind of make sense? I hope you've seen something like this, maybe in different notation before. I want to say, or limit as n goes to infinity of x sub n is 0, for instance, here. And here, too, I want to say something like limit as n goes to infinity of s sub n. Right? And so one of the things that perhaps is nice is to say, so we want something like this. Okay, is something. Okay, first we would like to be able to make sense of this expression, and then once we have as a meaning as to what this should mean, we would like to be able to say what this is. You might have seen this written as sum as n goes from 1 to infinity. Okay, something like this, or maybe plugging in this x sub n. Also, we have this. How many of you have seen this before, this expression? Okay, most of you. And so what is the value of this? Infinity. Okay. So somehow you see this is something that doesn't actually make sense as a real number, but we still would like to be able to write this and make sense of this. And indeed, let me introduce this as well. This perhaps is better denoted by zeta of 1. So this is a family, zeta family of numbers, or rather a formal series. And it turns out to be one of the most important mathematical objects, in fact. So you say, in general, zeta of s is the sum as n goes from 1 to infinity, or of 1 over n to the s. This is what is called the Riemann zeta function. Okay. Okay. Now, formally, this is not quite a function. At 1, for instance, it doesn't really converge to a specific number. But perhaps you've seen that, oh, this is like, so if I were to use for s maybe 2, then it would converge to something. There's like these tests and stuff like that. I'm saying all this, we're not going to be focused on these kind of matters for now. But the last part of this course is going to be all about making sense of these sums of, or making sense of these infinite sums. This is the part where we're going to talk about infinite series of numbers and also functions. Okay? Okay. So we have this. Here's another example. Let me give an example of a sequence of functions. Okay? Sequences of numbers is going to be important immediately, and sequences of functions is going to be important. So this time, because I'm looking at the sequence of functions, I'm going to denote it by f bullet. Okay? So for instance, I can say this. Now this is a sequence of functions defined on the closed and bounded interval 0, 1, taking real values. Okay? Send n to that function that takes an x and sends it to x to the n divided by n factorial. Okay? So we have two of these now. The syntax perhaps is more complicated, but what is this supposed to mean? It means this. F bullet, initially, I want to think of it as a function of n, but once I fix a time n, f sub n should be a function in and of itself, which takes an x value from 0, 1. Okay? So again, writing it explicitly, this really means for any n, f sub n is the function from 0, 1 to r defined by f sub n of x, okay, equals x to the n divided by n factorial for any x in 0, 1. This notation just compresses this statement. Okay? How do I visualize this? Again, there are multiple methods, but perhaps you would agree with me that this time something like this is going to be more complicated. So what you do, or what I would do is, for each n, I would just plot the graph of f sub n on the same picture. Okay? And so here's 0, 1. So for instance, f sub 1, right? F sub 1 is a function that takes x to x. So it's a diagonal function. Okay. F sub 2 is the function that takes x to x squared divided by 2. So now it's a parabola, but it doesn't go all the way up to 1. Right? So if this is 1, this is also 1. So somewhere here is 1 over 2. Okay. When n equals 3, f sub 3 of x is x to the 3 divided by 3 factorial. So it's even lower this time, right? So 3 factorial is 2 times 3. So the maximum height is going to be 1 over 6. But because f sub 3 is of third order, it's going to be even more curved compared to the parabola. I hope you would agree with me that we're really transitioning to calculus at this stage. So all that intuition that you obtain from calculus courses, and now I hope is going to start coming handy. And it keeps going on and on like this. Okay? Any comments or questions about this? Now the complication you see is this. When it comes to a sequence of functions, just like we talked about convergence of sequences of numbers, we would like to be able to talk about convergence of sequences of functions. But it turns out that there are multiple distinct ways of talking about convergence of sequences of functions. And so we're going to see at least two different senses. One of them is going to be pointwise convergence. Another one is going to be called uniform convergence. And so this is where things are going to get complicated. Somehow, when it comes to sequences of functions, a sequence can converge with respect to one sense, but not with respect to some other sense, perhaps. Yeah.
Is this function the n goes to infinity?
Say again?
So in this definition, right,
Yes.
you didn't specify n.
Yeah, I was being lazy here, but yes, n in integers.
Any integer, or
Yes, that's how this is defined.
goes to infinity, or
What does it
one?
mean?
Just one?
For any n positive integer, I have one function. I have infinitely many functions.
Can you draw a graph like that for n equal 2?
This is the case when n equals 2.
Oh,
This whole thing is a term, is a second term. Okay? This was a sequence of numbers. The second term was a number. This is a sequence of functions. The second term is a function. But if I want to visualize it, I'm going to think of a function as a graph, as a shape. So this shape itself is the second term. Very good point, but this is where things start getting complicated, actually. Any other comments or questions? That's why, in a sense, I spent this much time in the first week talking about graphs and all that stuff. Okay? Now, just like I transitioned from this to this sequence of partial sums, I can do the same thing with that sequence of functions over there. Here's another example. Again, let me denote it by S bullet. It's going to be a sequence of functions. At time n, it's going to be the sum of the first n terms in the sequence, as before. So I should say in other words, S sub n of x is the sum k goes from 1 to n. At time k, f sub k of x is x to the k divided by k factorial. Okay? This in and of itself is a sequence of functions. Okay? Because I can add a bunch of these functions and I get another function and so on. Okay? And just like I asked over here, I would like to be able to say something like, oh, what is the limit of this as n goes to infinity? It turns out, for instance, again, this is the last part of this course. If you take n to infinity, so that now we have this infinite sum here, it turns into some other function, which is the exponential function. s sub n of x as n goes to infinity, whatever this limit means, should be the exponential function. Yes, it is the Taylor series. We're going to, along the way, we're going to realize, oh, the reason why this happens is somehow, if I had started with this, there's a way to turn this into sums like this. You just differentiate k times whatever. There's a certain formula. We're going to discuss all this, okay? How many of you have seen something like this before? E to the x is these guys, okay. So well, I guess I should say from 0. Yeah, let's start from 0 because otherwise we're missing a term. Okay. X to the 0 is just a constant function. So it should be like this. N from 0 to infinity. Infinity of x to the n divided by n factorial. We're going to make precise sense of what this means. We need to make sense of this. We need to make sense of this. We need to make sense of this. Yeah.
So because you changed it to be greater or equal to 0, wouldn't that also change the s point?
Yeah. Very good. I should start from k equals 0. You're right. Very nice. Okay. And then, in fact, what people do is, well, they say, for instance, if instead of this 0, 1, I had some other space, some other sets, where I can take exponents, powers, and I can divide by numbers, insofar as I can talk about the convergence of something like this, I can make sense of the exponential of whatever using this as a definition. And so then you look at differential equations, and they have expressions like exponential of a matrix. So this ends up being very useful. We're not going to deal with any of that, but at the very least, we're going to discuss this, certainly, rigorously. Okay? Comments or questions about any of this? So at this stage, I'm trying to paint a certain horizon where we're going with all this. I want to give one more example. We're not going to discuss it too much, but maybe in more advanced classes, you might see instances of this. I can look at sequences of numbers. I can look at sequences of functions. I can also look at sequences of sets. And now, perhaps I can use a bullet. Let's say -1 to 1. For each n, a sub n is going to be a certain subset of -1 to 1. And here's a sequence, for instance. I can say, perhaps, n at time n, this should be -1 over n, comma 1 over n, let's say, closed. And now this is a sequence of subsets. It's a sequence of intervals. Okay? These are all valid things to do. If I want, perhaps, I can even try to make sense of limit as n goes to infinity of a sub n. In this case, perhaps you would agree with me that the limit should be just 0 in the sense that the limit of this sequence should be the intersection of all of them somehow. This is kind of a vague idea. We're not going to really try to make sense of this limit in this class, but this is something people do. Okay? This is what is called the Hausdorff metric. You do take limits of sequences of sets. Not going to discuss this in further detail, but somehow, for instance, in computer vision, this ends up being rather useful, even though these kind of things seem like they're rather abstract matters. Okay. So somehow, in order to be able to talk about convergences and divergences of sequences like this, we would like to be able to, so in order to talk about these limits, we need some sort of a metric. Okay? So this is the main thing that we need to understand really first. And I want to define this metric property or metric structure rigorously. Any comments or questions about any of these examples? Now, if you look at the textbook, they do define this notion of a metric, but typically it's in the second part of the course. So I'm going to be diverging in this regard. The point of defining this notion of a metric more generally is because we're going to be looking at convergences of sequences of functions simultaneously with convergences of sequences of numbers. And because, like I told you, there are multiple ways in which one can think about the convergence of a sequence of functions, in my estimation, it ends up being useful to parse what is really happening. The two convergences that we're going to be interested in when it comes to sequences of functions is going to be pointwise convergence, uniform convergence. What you should keep in mind is uniform convergence is with respect to a metric, okay? It is the right notion of convergence, okay? That's what we're going to want almost always. Sometimes it's going to fail, okay? Then we're going to try to go for this worst sense of convergence, which is going to be this pointwise convergence. We're going to make sense of all of these later. Okay, so now I need to define the notion of a metric space or metric function. Let me perhaps try to give some intuition as to why the notion of a metric is rather natural. Let's start with this. Let X be a set. Okay. Somehow I need to. So what I'm trying to do is I'm trying to come up with the right formalism that abstracts out the notion of a distance. This is what we're trying to understand. This is what we're trying to formalize. Okay. And of course, we start from the beginning. If I had the line, the real line, and if I had 2 points, how could I make sense of the distance between them intuitively? I say this is x. well, even before that, let's say this is 5, this is 10. What is this distance between them?
10 minus 5, 5.
So you would say, oh, it's the difference between them, right? So the distance should be 5. Okay. So ultimately, this is, in a sense, right. But this is one instance where somehow single variable doesn't really do justice. Let's try to switch over to 2 dimensions. Now I have 2 points on the plane. How can I make sense of the distance?
Different ways to interpret it.
Yes, there are different ways, but what is the standard way? What is the natural way, perhaps?
Euclidean distance.
Can do Euclidean distance. Was that what you were going to say as well?
No, it's fine. I was gonna say the slope, but that's.
Oh, okay, you can do that too, but that's more complicated. Okay, so what you do is this. Okay, essentially you draw this line segment connecting the 2 points, and then you say, oh, this is pretty much like an interval. Look at the length of this, right? So somehow then, the notion of a distance formally should be a function on your set X that takes 2 points. You cannot just say distance of whatever. You need to take 2 things. And you're going to talk about the distance between the 2 things. And ultimately, distance should be a non-negative number. You cannot say, oh, given 2 points, the distance between them is minus 17. That kind of doesn't make sense that much. There are other instances where this is reasonable, but not for us. So at the very least, this notion of a distance formally should be a function like so. And because it's a distance, I'm going to call it d. Okay? So I want to say, for instance, here, 5 is the distance between 5 and 10, for instance. Okay? In this case, if I had, let's say, 1, 2, and then 3, 4, right? How do you compute this distance? You say, you do the Pythagorean whatever. You say, oh, this length is 2, and this length is 2 as well. And then Pythagorean theorem, whatever, tells you that this should be 2 root 2. Then you would say, oh, the distance between these 2 points is 2 root 2. Okay. Now things get a little bit complicated. When we're sort of trying to abstract out the proper notions. First of all is this, okay? This is, again, not very important from a technical point of view, but it's something that is commonly assumed. When you're trying to formalize something like this, while in principle, distance between 5 and 10 should be the same thing as distance between 10 and 5. Abstractly, you would need to formalize that. I would write something like this, for instance. What does this mean? This means that if you're trying to measure the distance between 2 points in your space, it shouldn't matter where you start measuring. Right? You can measure the distance between these 2 by using your measuring tape this way or this way. It's going to give you the same thing. And likewise here too. You can measure this way or this way. Okay? That's an intuitive idea, but formally we have to write it out. Okay? The third property, or rather the second property that is really the core, is what is called the triangular inequality. It's not that straightforward to see it in one dimensions, but somehow if you look at what is happening on the plane, it becomes rather more apparent as far as I'm concerned. If you take 3 points on the plane, and you look at this triangle, it is always the case that the sum of the lengths of any two dominates the length of the third one. If this has length A, this has length B, this has length C, then C is less than or equal to A plus B, no matter what the triangle is. Okay? And this is like symmetric in a sense. So B is dominated by A plus C, and A is dominated by B plus C. How many of you have seen something like this? Some of you. So this is like an idea from plane geometry, perhaps. How I can perhaps justify this from an intuitive point of view would be something like this. For instance, take this bottom side, okay? This is this. Now I'm going to imagine that this corner is not fixed, and there are hinges on these two corners. Okay? So that is to say, I get to move the A side around. With this point fixed, I get to rotate. And likewise, I get to rotate this B side. This would be a triangle insofar as when I fold this side down and fold this side down, there is a common intersection. Okay. Fold it down. When I just rotate, this length 2 has to be A. And again, if I fold this down, something like this, this length is going to be B. So there has to be an overlap. The fact that the length of A, or rather this rod and this rod, have an overlap corresponds to the fact that A plus B, in terms of lengths, dominates C. This is the intuitive idea. And the geniuses that came before us realized this is really the thing that makes a lot of things work abstractly. Okay? And this is what is called the triangular inequality. In abstract, we're just going to demand that our D function satisfies this. And you're going to see the power of this. This is like a very simple idea, but it's going to make a lot of things work. Okay? Any comments or questions about this?
So it has two properties.
There's one more. I'm going to write it. Yes, but the triangular inequality is the main one. Without the triangular inequality, everything breaks down.
Why do you put an equal sign there?
Because, for instance, in one dimension, it's like I wouldn't be able to draw something like this. But given any 3 points in one dimension, this inequality still works. So it's not necessarily strict. Or you could also say, in principle, I would like to sort of, let's say, think of this as sort of like a degenerate triangle also. Triangle with 0 area, perhaps.
Then it's equal.
Yeah, then it could be equal. Yes. Now, the part where these things start getting complicated is that once we switch over to pure math, these points are going to be functions. And so triangular inequality is going to be about functions. This is going to be a function, this is going to be a function, and this is going to be a function. And somehow we're going to need to make sense of this triangular inequality, which is like this intuitive idea, in abstract. Okay? Just like in week 1 we had this abstract vertical line test, now we're going to have essentially abstract triangular inequality. Okay? I'm saying all this to prepare you. The third property, before even writing this down, again, this is not something super important as far as I'm concerned, but it's something very natural again. You want to say something like, well, the distance between any point to itself is 0. Again, kind of intuitive, but because we're trying to formalize this idea, we need to be able to say what d of x comma x is. What is the distance of x to itself? There are other cases where you don't want this, for instance, but not for us. For us, things are going to be rather intuitive in that sense. Even though we're doing abstract pure math, a lot of our assumptions are going to be tightly connected to intuition. In certain other areas, you end up needing to change your intuition so as to be able to do the math. OK. So here's the formal definition now. X be a set, okay? It's an arbitrary set. Then a distance function or metric. It's something that allows you to measure things, right? Measure distances. Is a function d, which is a function like so. X times x, taking values in non-negative reals, satisfying the following 3 axioms. I'm going to write them in the order of importance. First, I want to write the triangular inequality. Okay. This is our most important inequality. In this class, we're going to keep using this over and over again. Triangular inequality. For any x, y, z in x, distance between x and y is dominated by distance between x and z and distance between z and y. That is the formal way of writing the triangular inequality. So you want to think of x, y, z as the corners of this triangle. Second one is what is called the symmetry property. For any 2 points in x, distance between x and y should be the same thing as the distance between y and x. Doesn't matter from where you start measuring the distance. And then the third one is the so-called reflexivity property, which says, or maybe point separation, let's call it. Distance of a point to itself is 0, and vice versa too. If 2 points have 0 distance, they're actually the same point. Point separation. For any x, y, and x, distance between x and y is 0 if and only if x is equal to y. Okay. These are the three axioms. The main one is this. These are rather technical. Triangular inequality is going to be the workhorse in this course. Okay, that's it for today. We're going to continue on Friday. Thank you. All right, let's start. Good morning. So we had talked about metric spaces. I gave you the definition. The idea is basically this triangular inequality. I defined a metric or a distance function, but when you have a set together with a metric, you call it a metric space, this pair. So we're going to switch today to the notion of convergence for sequences. I'm going to give the general definition, but really for the next problem set I'm going to release today, it's going to be all about sequences of real numbers, their convergence, and so on. But later on, this more general approach is going to help us because eventually we're going to start thinking about convergences of sequences of functions. And then you're going to start appreciating this more abstract approach more as far as I'm concerned. That's my speculation at the very least. I want to say a couple words about the first problem set, other things. So there was an issue with Canvas yesterday, as far as I understand. Some people got unenrolled from classes on Canvas. And these kind of things happen, okay? Part of why I do the things I do is so that in case something goes wrong, we're going to be able to still continue as usual. So for instance, if you go on Canvas, even though we have all these PDF files, you can download them if you so prefer. I have also sent an email about alternative links yesterday. Did you all receive this? OK, so there's a GitHub repository in my name. So that's almost always going to be available. And I'm going to try to keep it updated. YouTube videos, again, unless something goes terribly wrong, end up being rather stable. But if something goes wrong with accessibility and stuff, it would be really helpful if you could send me an email saying, oh, there's an issue and stuff like that. Yesterday, I received emails from both students in this class and the other class that I'm teaching right now, so that was helpful. I have graded, me and our grader graded the first problem set. The grades are on Canvas, but yesterday, as I tried to import the grades on Canvas, and it still didn't quite work. So I'm going to wait until everything settles down, and I'm going to try again. But at this point, you can at the very least go on Gradescope. I think the enrollments on Gradescope are fine, and you can see. Another thing is that if you go on Canvas or the GitHub repository, there's now a new PDF file collecting some selected solutions that I write myself. And so typically, if I'm grading a problem for accuracy in a problem set, I'm going to be writing a detailed solution to that problem as well, so that you guys have an idea as to what type of responses I'm expecting in general. Of course, I'm not going to expect you to go as much detail as I go in these solutions, but I think a big part of this class, instead of trying to describe what I'm expecting, it's better if I lead by example. So that's all I wanted to say. I want to say a couple words about the feedback I received. So as you know, one part of the submission procedure is this Google form. Now, I'm not going to spend time every week going through these kind of things, but I wanted to clarify and ensure that I am reading what you're writing and stuff like that. So this sort of gives me a general idea as to where we are. So for instance, one question was, in terms of mathematical foundations, which category do you fall into? So basically, the class splits 50-50, less comfortable, and in between. And there's a couple of people who are more comfortable. Experience with mathematical proofs. that's kind of surprising, but the majority of the students have some experience, presumably from discrete math. Yeah, so last time I taught this, it wasn't like this, for instance. So it's good in a sense, right, like proofs, but at the same time, the types of proofs that we're doing in these classes are kind of different also. So many students have taken 5+ classes in this course. 50%, that's a lot of good experience. And so while we're doing math in a different way, ultimately, my understanding would be that, it's going to help. Favorite topics, integration methods, flux and divergence. Unfortunately, we're not going to be able to do because these kind of things are multivariable, and this is all about single variable. Taylor series, that we're going to do. So this course is application. It's not application oriented. And some people wrote differential equations. I mean, I agree. Like, even though I'm a pure mathematician, really calculus starts making sense once you start thinking about differential equations. There is going to be some differential equations, but at the very least, they're going to be implicit. Likewise, optimization. You can imagine things like sup and inf as some sort of an optimization procedure in some sense. But when you're talking about optimization, you want things like Lagrange multipliers and stuff like that, and we're definitely not going to go there. Stokes' theorem, again, this is like a multivariable thing, but of course we're going to do fundamental theorem of calculus. A couple people wrote L'Hopital's rule. That's a very convenient sort of trick, and there's a proof in the textbook. Okay, last time I taught this class, I proved it, but I think this time I'm going to skip it because for whatever reason, it just thematically doesn't fit into most of the other things we're going to do. So the proof is a certain thing, but then we don't end up using the same method of proof or something similar in the rest of the course. When you go over to something like distributions and stuff like that, then it starts making more sense, which probably we're not going to do. Okay. So basically 50%, slightly less than 50% of students taking this course are going to take the sequel course, which is really a lot harder than this. But I'm going to try to sort of make some comparisons every once in a while. I'm going to say, oh, in single variable, this theorem works this way. For instance, like inverse function theorem. But in multivariable, there is, again, an analogous theorem, but it's going to be more complicated and stuff. OK. In terms of when you guys started having a look at this problem set, I think the distribution is fairly good. You want to have a look as soon as possible. On the other hand, when it comes to dedicating focused time, I would say you want to start at least by Tuesday. Like, first problem set was, maybe you could get away with it, but when things switch over to calculus, it's going to get rather nasty, okay? So you see, we're going to start using epsilons and deltas and stuff like that. And okay. Approximately how many hours? I like this distribution. A couple of people spent more than 10 hours. So I would suggest something like this. And this is also, I'm trying to give you some idea as to how we're grading the problem sets. I want to prioritize the amount of time you spend thinking about these problems. Okay? Instead of performance, I want experience. And so approximately 10 hours a week per problem set, I think is reasonable and expected. You should expect this. And I would say allocate your time in your mind and just spend some equal amount of time on each problem given. Okay? Don't prioritize completing one problem as opposed to distributing your time almost equally. Okay? So this is partially to destigmatize the idea of not being able to solve a problem. Okay? In a in an earlier class, either you can solve the integral or not, okay? And you are expected to be able to compute, do integration by parts, whatever. Now we're trying to really build mathematical maturity, and that ultimately ends up being related to building resilience, okay? How far can you go if you don't quite understand everything, okay? Or maybe you understand a piece of the puzzle. And so, for instance, when I asked, classify the problems, easy, challenging, overwhelming, and then there's another option, didn't work on it, ultimately, I don't want to see didn't work on it, okay? Work on every single problem just a little bit. Have something to say. These more personal things I'm going to skip. I'm going to look at that myself. Now, there was this other problem, question about AI use. If you used AI, I was asking you, where exactly did AI help, and where do you think AI ultimately will not be able to replace you? Now, I like most of the answers that I saw, but I would rather you focus more on specifics. Like, I don't want you to make like philosophical statements about how AI can't replace us, or how AI is going to replace us, or whatever. For each problem that you use AI for, say it's like, in this part, this was really sort of like grunt work, and like AI could help with this, but then I asked this part, and it's like it said some stuff, and it was more of a, how to say, it ended up wasting my time more. So try to be specific. Part of it, of course, is that I don't quite know what's going to happen in the future regarding AI, but some people who seem to know what they're talking about, they are taking these kind of things very seriously. Some people think, it's going to hit a limit, and like it's not going to go beyond that limit. But I would rather, no matter what you end up doing eventually after you graduate, I would rather you get something out of this class that is transferable to this bizarre time, say. Okay. Any comments or questions about anything? So for instance, the second part, so part B of problem 6 about the surjunctivity, that was a statement that I asked AI to generate. Okay, so part of it was, it sounds right, of course, and many of you fell for it. And initially I fell for it too. Like at first, I was like, yeah, whatever, and then like a couple hours later, I'm like, hang on a minute, it's like I can think of a situation. And part of it, of course, is that the first problem set was partially about logic. So it's like, if this is not this or that, whatever, it's like that sort of, I think, made things a little bit complicated too. But some of you did catch that the second part of the sixth problem is not quite correct. It works one way only. Okay, so these are all I wanted to, this is all I wanted to say. Are there any questions or comments about this? Yeah, some of you have contacted me. The minority, there's a minority that wasn't able to submit work for problem set 1. Some of you did contact. If you're one of those who had issues, submitting work and stuff like that, I would be happy to, meet in person, discuss all these things. Okay. Okay. So back to convergence, back to sequences, metric spaces, and all that. So a metric space is a set together with a specified distance function or metric d, and we typically write it like so, x comma d. Here are two exercises. We had talked about this last time. If x is the reals, then the standard Euclidean or standard or the Euclidean metric is this function, right? So you take 2 points in your real line, and the distance between them should be their difference. Except that you want to put absolute values, because otherwise, if, for instance, x were 0 and y were 5, you would want the distance to be 5, not minus 5. And so you put absolute values here. Now it's a metric. Okay. I want you to verify the axioms. And so, for instance, just to reiterate, the main thing is the so-called triangular inequality. And if you write it for this specific function, it looks like this. Okay? So, x minus y in absolute value is dominated by x minus z in absolute value plus z minus y in absolute value. When you're having a look at the textbook and stuff, you're going to see this because in the textbook they don't introduce this notion until much later. But in my own experience, instead of looking at something like this and sort of reading this as, oh, the absolute value of the difference of x and z, it becomes more useful to think of this expression as the distance between x and z. This is like a minor psychological difference, but it really makes a big difference as far as I'm concerned. Another exercise I'm going to leave to you is that if you have a metric on your whatever set, then you have what is called a reverse triangular inequality, which says this. The difference, or rather the distance between the distances between x and y and x and z is dominated by the distance between y and z. This really follows from triangular inequality. You need to just move things around a little bit. So for instance, if I were to write this expression for this guy, it looks like so. So this reverse triangular inequality looks like this. Okay, so whenever I see d of x, y, I'm going to replace it by x minus y in absolute value. I have this minus x minus c in absolute value. All this in absolute value is less than or equal to y minus z in absolute value. I don't know about you, but I think this formula is a lot more pleasant than this formula. This double absolute values and stuff make me scared a little bit. Your mileage may vary, but it's up to you. Okay. Any comments or questions about this?
Your notation
Yes.
about a parenthesis that has an X as a set and then write D.
Yes.
What does it mean?
Yeah, I mean, I knew you were going to ask this. Yes. Your colleague is suggesting, like, we use this notation, but then this should be an element of some product set. So there should be something like the set of all sets that I'm taking x from. You can think of it that way. You can say, if you want to be slightly more sort of robust, logically speaking, you could say that this capital X, it being a set, is coming from the class or category of all sets. And this is a function of this type. Typically, people would say a metric space is a pair, x comma d, where capital X is a set and d is a metric on x. Yeah. So they would typically sort of suppress the idea that, oh, you're taking this first argument from some space of sets somehow. They would just like put it aside, not mention it, because makes things complicated. And indeed, often what you would see is they would say, let X be a metric space. Instead of writing this, they would just write capital X and call it a metric space and suppress this D. Okay? So for instance, when I write R, I really mean it's the field. It has like a bunch of things. So R plus, minus, times, divided, and less than or equal to. These are all the extra structures that I'm actually using when I use R, but I just suppress all this. Okay? Yeah. This is just how people use these types of notations. Any other comments or questions? Okay. So if I have a metric space, and if I take a sequence in it, remember this X bullet notation denoted for me a sequence. And how do I think of this? X bullet is basically a point in my metric space that moves in time. And my time is discrete. That's sort of the heuristic. More explicitly, this X bullet is nothing but a function from integers, or let's say non-negative integers, into X. You see, by using this bullet notation, I'm suppressing all this stuff. Like, I don't want to say, oh, I'm specifically starting at 0. It's like, what is n? I don't want to deal with any of this. I say X bullet, and like everything else is going to be a dummy variable that I don't want to deal with. All I want to call is the name of the sequence, and that's X. And then I take an X infinity. Okay, this is a specific point. Then I'm going to say, I'm going to call X bullet to converge the X infinity if you have this so-called epsilon delta, essentially, statement. For any epsilon, there is an n integer such that after this n, the distance between xn and x infinity is less than epsilon. Okay? In a second, I'm going to give some heuristic as to why this seems to capture the notion of convergence. Okay? But for now, this is the formal way of defining convergence. In this case, we also write x bullet arrow x infinity, or limit as n goes to infinity, x sub n equals x sub infinity. Okay, these are like shorter ways or faster ways of writing this. And then I'm going to say x bullet is convergent if it converges to some point, and if it doesn't converge to any point, it's called divergence. Okay. So here's the heuristic as to why this is the right thing to look into. Okay. Here's my metric space. Okay, I'm going to draw it as a blob. You can think of it as the reals, as a subset of reals, whatever. Okay. Somehow, for me, trying to visualize what is happening in one dimension is harder. Somehow, looking at sort of planar caricatures end up being more intuitive in a sense. So let's first try to imagine x bullets. I have n equals 0 gives me x0. That's 1 point. N equals 1. At time 1, I have possibly I'm at a possibly different point. So I have something like this. I'll do this. So let's say at time 0, I'm here. It's a point. Okay? Then at time 1, say I transitioned over there. I jumped over there. Then I jump again. This is where I'm at time 2. Keeps going on and on. Okay? Maybe I repeat a couple times. Okay, something like this. jump like this. Let's say go back, and then you jump back and forth a couple times. And then you jump here. And then you keep going on, okay? The point is, the moment you see the word sequence, you now have this dynamical object that has a future, okay? Time goes to positive infinity. You say that your sequence converges if, as you take time to infinity, your motion stabilizes. Okay? Here's what I mean. I'll draw another picture here. Again, this is my x. I have this x bullet sequence, and I'm saying, oh, now I have this target, in fact. Think of x infinity as your target. Here it is. X infinity doesn't move, okay? It's a stationary point. It is a stationary state. X bullet moves, x infinity doesn't move in time. What does it mean? What would it mean for x bullet to stabilize at x infinity? It would be something like this. Initially, I don't know what this guy is doing. Maybe there's some fluctuations and stuff like that. What I want to say is that as time goes to infinity, my terms are going to be near x infinity. And then I say, well, I could ask x sub n to be x infinity on the nose, hitting the target on the nose, okay, exactly at x infinity. But it turns out that this is almost never useful. And this is where, in a sense, calculus differs from something like algebra. We don't really worry that much about hitting things exactly. We worry rather about approximating things. So I want to say, I'm not necessarily trying to hit the bullseye. This is my bullseye, imagine. But I want to be as close to it as possible. And so I take an error margin. And that I'm going to call epsilon. Okay? Epsilon is my error margin. And then I look at this. I consider a bullseye centered at x infinity, at this target, of, let's say, radius epsilon. So it's a little ball like this. And in fact, let's say epsilon is 1 first. I fix my epsilon first. I'm saying with an error margin of 1, I want to be near x infinity. Okay? So now I switch over to my dynamic object, my sequence. Again, like I said, initially there could be some fluctuations and stuff like that. I have to get rid of the initial n terms, initial capital N terms. But what I do need is that after some finite time, which is this capital N, I would want a guarantee that I will be always within one of my targets. So I don't care what happens the first couple times. Maybe it goes like this, whatever. But eventually, okay, maybe you sort of like get close and then you get away a couple times. But eventually, you want to guarantee that you're always staying within. Just make sense of this. Let's do something like this, perhaps. Maybe jump there, whatever. Okay, escape, get close, escape, get close, and now you're trapped. You're trapped to be at most one distance from your target. Okay? So for instance, in this case, what I'm saying is, for epsilon equals 1, let's say we start at time 0. So this is where I'm at time 0, time 1, and so on. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, at 18. Okay? After time 18, I know I'm going to be within 1. I waited until time 18 in this specific case. And then after that time, I know that this is going to be the upper bound on my error. Wait until capital N equals 18 to ensure an upper bound of 1 on the error. At most epsilon error. Okay. Any questions about this? This intuition works in any metric space. Forget about real numbers. It works when this X is a set of, when this X is a space of functions. Your terms now are functions and so on. It always works, this intuition. Yeah?
So because it says for all epsilon, I assume it's like, the idea is you can keep picking further times and there will be smaller epsilons.
Exactly.
Okay.
Exactly.
Yes, makes sense.
We're not done, okay? This is the first step. The point is, it doesn't say for some epsilon this happens. It says for any epsilon this happens. Okay? Because ultimately, okay, epsilon equals 1 is an upper bound on the error. But if possible, you would rather have the error margin to be lesser. Okay? So this time, what I do is this. I say, OK, this is good. If I wait until time n, I guarantee an upper bound of 1 on the error. But now let's say I want my error to be now 1 over 2. OK? I am being now more strict. I'm expecting more things from myself, or from my sequence. So now, again, the center of the ball, if you want, is at x infinity. And instead of looking at radius 1, I'm looking at radius 1/2. Okay? Now, I didn't keep drawing, but in this picture, maybe what happened is, OK, so I was guaranteed to be within 1 after time n, but then after this point, maybe I kept moving here. I was like outside. That won't do. That won't do for convergence. When I shrink my error margin, again, I want my sequence to rise up to the occasion and say, oh, OK, if you want a smaller error margin, then I might need more time. OK? But again, I'm going to achieve this error margin you're asking me. OK? And this is exactly what your colleague was suggesting. In principle, you should expect that as you decrease epsilon, which is what you want, quite possibly this time that you have to wait until you can achieve this error margin is going to increase. It doesn't need to in principle, but it could. Okay? So this doesn't say there is some time such that it works for all error margins. Depending on what error margin you want, you need to engineer your time to wait. Okay? If you want more, if you want better, smaller error margin, that means that probably you're going to have to wait more. You have to be more patient. Comments or questions so far?
So if I'm trying to prove that a given sequence converges, I need to prove that any epsilon, for any epsilon, that it will keep being inside of that smaller area as time goes on.
Yeah. Yeah, you're going to say let epsilon be arbitrary. Then you're going to do some math, engineer some time that guarantees this bound after that time. This works for numbers, this works for sequences, this works for pretty much everything, at least in this class. Okay. So you see, when I look at these statements, I'm not reading the logical statements. I'm sort of interpreting what is being done here. Okay? Because, I told you when you see a sequence, think of this as time and stuff. But time is not a mathematical thing, really. It's not a formal idea. It's a story. Okay?
When you first define a metric space,
Yes.
there's no number involved like epsilon. And now you jump here and tell me there is an epsilon. That is strange.
Well, that's a good point. And this is one of the benefits of using metrics. Okay? Like your colleague is suggesting, X, capital X itself, is not necessarily a bunch of numbers. But this metric, notion of a metric that we defined abstractly, you feed to it 2 points in your space, gives you back a number.
But the definition didn't. You just say that the relative distance, something has to be between something. You define it that way.
What do you mean? Here?
Yeah,
This is not the definition.
the matrix space definition is there.
No. This is not the definition of a metric space. This is an exercise. This is the hypothesis. What I did was I didn't write down explicitly a metric space is this. I just pointed out that I was using that definition here already. I skipped defining a metric space explicitly. Because what matters is having a distance function on your set.
So D is a value, or D is a
D is a metric. OK, I'll write it. This is really nice because usually I am the more sort of careful person when it comes to, doing math. So, definition. A metric space, that's the definition, is a pair X, comma D, where X is a set and D is a metric on X. What is a metric? That we defined last time. Does this kind of clarify things a little bit, perhaps? No? Maybe we can discuss the foundational aspects later. OK. Any other comments about this intuition, though? Yeah.
So for any set, whatever, if you have like a set of sets, if you can define a distance thing between two of them at all, such that the three things are true, you can have a convergence no matter what.
Which means that you can pretty much do calculus with anything. Yeah. Yeah. Yeah.
So
Yes.
you can define the distance between apple and orange?
Depending on the context, yes. So probably, from a biological point of view, I would like to think of them as species, right? And so, assuming evolution, there's a tree. And based on tree structures, we have metrics. So, or like if you have a family of people, you can talk about difference or distances between them, not in terms of their physical distance, perhaps, but how far you need to go back in the ancestry to find a common ancestor. That would be sort of the appropriate distance in that sense. We're not going to use any of that. So there's a more advanced version of this course where we just take metric spaces abstractly. We're not going to do that. We're going to use either this as the metric space, or some space of functions taking real values. These are going to be the only two metric spaces that we're going to be interested in. I mean, I understand what perhaps you're getting at. This is such a general thing that it applies everywhere. And that is indeed true. And that's why this idea of a metric space is so useful. Then, if you go to physics, even though I don't know much about these kind of things, there's something called the Einstein field equations. You set up a certain partial differential equation whose solution is a certain metric. Okay, it's not exactly a metric in this sense, but it's a metric in some sense that is somewhat related. And somehow that represents matter, how it is distributed and stuff. This idea of a metric is one of the most useful and important concepts in all of math and beyond. Yes. I will switch over to examples in a second. And like I said, in the next problem set I'm going to distribute, it's going to be all about sequences of real numbers to begin with. Eventually, we're going to start talking about sequences of functions, what it means for them to converge, and so on. But for now, we're just going to focus on this case. But this is the intuition, OK? You have a dynamical object, your sequence, you have a target. You're trying to say something like, oh, my dynamical object stabilizes near this target. That's always the intuition. OK. So for instance, I can look at this sequence of real numbers. Let's say x bullet takes n to 1 over n. Okay. So this is a sequence of real numbers. If you want to be explicit, you want to say something like, oh, my time starts at 1, and this goes from positive integers into reals. If you want, you can write it like so. And certainly, this should go to 0. Right? 1 over n, 1 over 2, 1 over 3, 1 over 4, whatever, it should go to 0. Well, the idea or the claim is that x bullet converges to 0 using this notation. I'm saying, based on this intuition, this sequence stabilizes at 0. If I want, I can use this notation as well. It's the same thing as writing limit as n goes to infinity of 1 over n equals 0. This is the same thing as writing this. This is the same thing as writing this. And that's the claim for now. We need to prove this statement. Let's prove it. Let epsilon be positive. What do I need? I need some time, capital N, such that after this time, the distance between 1 over n and my target 0 is at most epsilon. OK? So I'll write it here. Want there is an n such that for any lowercase n after uppercase n, just rewriting this in this context just says x sub n minus x sub infinity in absolute value. But when you plug in the things, this just turns into 1 over n. And I want this to be less than epsilon. OK? This is really what I want. But you see, here is where I can use one of these axioms. Epsilon is a positive number. By the Archimedean property, I know that there is some capital N such that this happens. There is an N such that this happens. This is Archimedean property. Okay. Well, I also know that if lowercase n were any integer greater than n, its reciprocal would be even less than this by basic algebra. Then for any lowercase n after uppercase n, right, so you take the reciprocal, 1 over n upper bounds, 1 over lowercase n. But I had chosen this uppercase n so that 1 over n is less than epsilon, which means that after this uppercase n, 1 over n is always going to be bounded by epsilon. And this is x sub n. And this is what I wanted to prove. Let's try to adapt this picture that we have over here to that situation as well, so that you have some sense as to how I sort of visualize these kind of matters. We had talked about how to visualize sequences of real numbers. And in fact, we had talked about this specific example last time. Right? So I have this. This is my time parameter. And this is the reals, space parameter. And I have these discrete times. Okay. Then it's going to fit into this hyperbola type of thing. So this is time 1, 2, 3, 4, 5, and so on. Okay. And this is x bullet. 1, 1 over 2, 1 over 3, and so on. As I take time to infinity, right, I'm going that direction in the horizontal axis. I want to say, well, this sequence of points stabilizes at height 0. Okay. What did I do here? Ultimately, what I said is this. I said, let me let an epsilon to be positive. See, this is my target. Height 0. This is my target. Okay. I'm going to take an epsilon. Now I have an error margin like this. In one dimension, I need to say positive, so plus epsilon or minus epsilon. So I have this band of height 2 epsilon here, centered at height 0. Well, based on this picture, you could say, well, this keeps going down and down and down. If I eventually wait long enough, it's going to stay within this band. Right? So it's going to stay within this band, maybe at this point. And once I catch the term of my sequence to be within an epsilon, it's going to stay within this band. Okay. So this picture is sort of like the heuristic behind this argument that corresponds to this more general picture.
Do you not also need to prove that 1 over n always greater than 0? So
No.
You prove that it's decreasing always, but
No, exactly. Because in the idea of convergence, I said I don't really care about hitting exactly the target, but if I am, then things are the way they are. They are better even. Okay. Okay. That's it for today. We're going to continue on Monday. Thank you.